So it's a great pleasure to introduce David, who is today's speaker. So David, in fact, is known to most of us from many years. He's just to introduce now, he did his bachelor's from Oxford and PhD from damned Cambridge. Then he did postdoc at Trinity College and University of Colorado. And David David works on various topics of MHD in fluids, astrophysical and geophysical applications, dynamo theory, turbulence, numerical modeling. So today he's going to tell us about inertia-less dynamos in rotating convection. David, all yours.
Okay, thank you, Mahendra. Thank you very much for the invitation and for the introduction. And thank you everyone for showing up, whether it's your dinner time or your lunch time. It's appreciated. Okay, so this is what I'm going to be talking about: inertialess dynamos in rotating convection. So this is work I've been doing and I'm still doing with Fausto Catania, who is a long-standing collaborator. There are these papers, if you're interested. I put this in the question mark. This is work we're about to submit, but you know, it's to science, so it'll probably be rejected almost straight away. So it's a speculative paper. I'll just say a little bit about that at some stage today. Okay, so let me tackle these various words in the title first of all. So let me make it. Let me explain first of all exactly what I mean by the neglect of inertia, because it can mean a few things, I think. So what I mean by the neglect of inertia, and I'll say why we do this, but let me just say what it is for the minute. It's the neglect of both acceleration terms in the equation of motion. So we're going to neglect the whole total derivative of the velocity, both terms du by dt and u dot grad u, in comparison with the Coriolis term. Okay. So as we'll see, the left-hand side of the equation of motion, of course, so we'll have no time derivatives, and that's significant. So why should we want to do that? Well, two reasons. One is that in rapidly rotating bodies, if you looked at how big these acceleration terms are compared to the Coriolis terms, which is the Rossby number, that's quite small. So we have for example, in the Earth's outer core, we have an estimate of the Rossby number. Of course, we know the period very well. What we don't know quite so well are things like the velocity, but we can get a measure of the velocity from looking at how fast magnetic features have moved in the past few hundred years. And so the ratio of time scales here is, this is obviously a day, and this is of the order of hundreds of years. And so the ratio, the Rossby number, the ratio of the two is quite small, 10 to the minus 5, 10 to the minus 6. So that's one reason why we might neglect inertia. The other is that, as I'm sure many of you know, I mean, it's very difficult to make progress in the study of nonlinear dynamos. And as I'll try and explain later, by throwing away this pesky nonlinear term, that allows us actually to make some progress, I think, in what we might say about nonlinear dynamos. So those are the two reasons. So I'm not going to be doing, a big spherical geodynamo simulation, but it's worth looking at what we know about the geodynamo and the balance of terms, because that's going to be behind everything that I'm going to be talking about, really. So I've already said that inertial terms are small. What about the viscous terms? So here's a standard argument that I'm sure many of you know well, but let me just go through it. So this is just hydrodynamics for the minute. Let me just talk about hydrodynamics, no magnetic field. Then in hydrodynamics, there's in a rapidly rotating fluid, then there's what's called a vac balance. So the three terms that come in are viscous, buoyancy, which we call Archimedean, so we can have an acronym, and Coriolis. And this is the picture that we have. This is taken from an old paper by Bussa, where you have essentially columns of depth LD and width LH, let's say. And under this balance, under this vac balance, then you can show quite straightforwardly that the width of the columns is order the Ekman number, which I'll say in a minute, the Ekman number to the third times the depth of the columns. And in the Earth, so this is the Ekman number, it's a ratio of viscous terms to rotational terms. Okay, in the Earth, this is a small number. 10 to the minus 15 is the number that you often see quoted. And so this suggests that LH, the horizontal scale of these motions, is 10 to the minus 5 times smaller than the depth, and the depth is something like the radius of the outer core. And this suggests that these columns are very thin. 20 meters is what you would get, for example. Does that matter? It matters because let's look at what that might then say about the dynamo. So you could work out a magnetic Reynolds number on that scale. Now we know from some theories and certainly lots of numerical results that for a dynamo to proceed, you need the magnetic Reynolds number, this U times a length times divided by the diffusion, magnetic diffusion, of the order of 1,000. It varies depending on the flow and the geometry, but that's a reasonable estimate. If you take the U that we know from the Earth and you take L as LH, then this is a very small number. Okay, it's 10 to the minus 2. And that's 5 orders of magnitude shy of what you need for a dynamo. And you can argue that we don't know eta all that well and we don't know U all that well, and that is true, but you've got to make up 5 orders of magnitude. And so there's something wrong, the Earth has a magnetic field, so the Earth certainly has a dynamo, that much we know for sure. And so what's gone wrong in this argument? The argument must be that the length scale actually isn't LH. Okay, it must be something bigger. And it must be much bigger. It must be orders of magnitude bigger to get Rm from this 10 to the minus 2 up to 10 to the 3. And the idea, which I'll talk about in much more detail, the idea is that this vac balance, you see what I talked about here is essentially a kinematic dynamo argument where the flow would be in vac balance. But you might argue, oh no, the magnetic field might come in and change the balance completely. And then you'd have what you might call Mach balance. So this would, in which you have a balance between magnetic buoyancy and Coriolis and no viscous. The viscous force is not important. These are known sometimes as strong field solutions. Sometimes they're known as Taylor states. And as I say here, it sounds good, but actually finding these guys is quite difficult. Okay. You might think, well, why should it do that? Do we have any reason for thinking that the Mach balance might even, why is that a viable option? So if you go to a simpler problem, this is old, but it's helpful, I think. If you go back to what is a simpler problem, which is rotating convection with an imposed field. So not a dynamo problem, a magnetoconvection problem. Then we've already seen this argument. So if you just have convection, no magnetic field, then you have narrow cells. We've just talked about this scale. And the critical Rayleigh number scales as Ekman number to the minus 4/3. Okay, so heavily dependent on the Ekman number. If you looked at another problem, which is magnetoconvection, no rotation, then the relevant dimensionless parameter there is the Chandrasekhar number. Chandrasekhar number is proportional to the field strength squared. It's very large if the field is large. And the critical scalings there are K is Q to the 6th. So again, you get a very thin cell. and the Rayleigh number goes like Q. So if you've got convection and you put rotation in, rotation is definitely stabilizing. If you've got convection and you put a magnetic field in, magnetic field is definitely stabilizing. Okay, the preferred mode becomes very narrow. And the interesting point here is if you put them together, and this is in Chandra's book, he doesn't make too much play of it in his book. It was looked at in more detail by El Tayeb and Roberts in a short paper by a much longer paper by El Tayeb back in 72. If you put them together, then a strong field can improve matters. If you've got rapidly rotating convection and you put in a strong field, then you lower the critical Rayleigh number from Ekman to the -4/3. Remember, Ekman is small, to Ekman -1. And crucially, you make this, that occurs when the scale is order 1. So the question that everyone, that's been asked for a long time is, can something like this happen when the field is self-generated? Okay. There, of course, it's much more sneaky because, the field does what it does in a dynamo. You don't have control over it like you do to some extent when you impose it. But that's a kind of reason why people think that these Mach solutions, might be there. And this is a picture that you often see. Looks like I can't spell Rayleigh. This is just a, sketch really taken from a paper by Paul Roberts a long time ago of what might be going on. So the x-axis here is the Rayleigh number. So convection is, all of this is convecting. The critical number for convection is way down here. Then you have a weak field branch of solutions. Okay, so these would be bifurcating from the zero state. And then you've got a strong field branch all the way up here, not connected to these guys at all. Okay, and you can see that if the strong field branch is subcritical, meaning it comes, the nose of that branch is below the dynamo branch here, then this is what the Earth, this is where the Earth must be. From that scaling argument, we decided this can't be where the Earth is, right? Because the Earth can't support this weak field branch, but it could support this strong field branch. So if it's anywhere, it's down here. Okay. And there's an interesting question. This is what we've been writing a speculative paper about, but as I say, probably we'll find out, maybe hard to publish, I don't know. How did the Earth get there? How did the Earth manage to get this strong field in the first place? Okay, because the Earth has been rotationally constrained all of its history, so it can't really have picked it up along the way. So it must have been there at the beginning, and that puts a constraint actually on theories of the Earth-Moon formation. There are lots of theories of how the Earth and Moon were formed, impact theories, but grazing impacts, or the other extreme where the Earth and Moon kind of almost come together in an Earth-Moon soup, and then the Moon spins out. And one thing which is never looked at, and the problem with these theories is that you can make all of these theories satisfy current, what we know about the Earth-Moon system today. But there is this extra bit of information that however it happened must have been such that there was a strong magnetic field at the beginning. Okay, and that's never really used. So we've written a paper saying, maybe you could use that, but that's all. It's interesting, but that's really all I'm going to say about that today. Okay, so how is dynamo modeling done? Well, I would say, I mean dynamo modeling in very rapidly rotating systems. So there's 3 possible approaches. One is that you solve the full equations, and that's a really computationally intensive task. Now, and the hope, of course, is that if you get to small enough Ekman numbers, you will get dynamos that look like the Earth, where the inertia terms and the viscous terms vanish. Now, most computational dynamo models, even at low Ekman numbers, the dynamos that emerge still have a lot of inertia terms and viscous terms. There's some evidence actually in the most recent ones by Schaefer, for example, that there is some evidence of Mach balance, but that is not completely clear. And of course, there's a huge gap between what is accessible today, even in with the most powerful computers, and the Ekman number of the Earth. So what I'm going to talk about, as I said, is we're going to throw away inertia, but I'm going to keep the viscous terms. Okay, then we can see how important they are. And the third one, which in some sense, sounds as if what one should do in some sense is to throw away inertia and viscosity from the beginning. We've argued that maybe they're not important in the Earth, so why not throw them away? Now it's interesting how that has gone. So this was, of course, a suggestion made by Brian Taylor back in 1963. This is what he came up with at that time. He said, if you do that, so you only have this equation. So this equation now has no inertia on the left and no viscosity on the right. It just has Lorentz force, buoyancy, and pressure. If you integrate this, if you integrate the azimuthal component of this around a cylinder, it must vanish. And so you have a constraint, so-called Taylor's constraint. Okay, the azimuthal components of the Lorentz force integrated around a cylinder, any cylinder, all cylinders, must vanish. And Taylor put forward a nice approach to solving the dynamo problem whilst keeping his constraint. And it's very elegant. And even though it's nearly 60 years since his paper, no one really has got it to work. Okay. So we're going for the middle ground here. So this is the problem we're going to look at. Okay. So it's geometrically simple, fluid dynamically simple in a way. It's rotating, Rayleigh-Bénard convection, rotating about the pole in a periodic box, periodic in the horizontal directions, simple boundary conditions, top and bottom. Simple, I mean stress-free, impermeable, fixed temperature, perfectly conducting. That's probably not crucial, but these are mathematically, computationally, the most convenient things you can do. So these are the equations. Boussin-esque, okay, to make life easy. And the key thing, of course, is that there's no inertia on the left. So in terms of solutions, how you solve, of course, you time step these two equations, and then you solve this equation. Okay, we don't have Taylor's constraint. We can actually solve it because we have the viscous term. If we didn't have the viscous term, we would have Taylor's constraint kicking in at this stage. But so we time step B and theta, and we solve for U at each stage. There's three parameters: the Ekman number, the Rayleigh number written. So in rotating problems, it's often helpful to have the rotation into your Rayleigh number. So it's the standard Rayleigh number times Ekman number, if you like. And this, which is called the Roberts number, ratio of thermal to magnetic diffusion. And there's the aspect ratio, but I'm not, provided that's wide enough, that's the key thing. Okay, so there's these three parameters. I'm going to fix the Ekman number actually, but we'll talk about that as we come to it. So what do you lose by having the inertialess system compared to the full system, the full Boussin-esque system? So if you like, you can consider it as infinite Prandtl number. If we had the Prandtl number, it would be 1 over Prandtl number times the Ekman number times the inertia terms in this scaling. So you can think of it as infinite Prandtl number. That's sometimes how it's described. Or let me just put this in as sort of an aside, an interesting aside, which kind of surprised us in a way. If you take the magnetic energy and kinetic energy, dimensional, let's say, and you scale them as we've scaled our variables. So B and U would would be what would come out of the code, then it's actually got a Prandtl number in it. So the magnetic energy to kinetic energy is not really defined at infinite Prandtl number. So in a way, you might think that's not such a surprise because we have no energy as such, right? Energy you normally think of, an energy equation you would normally think of as dotting the du by dt by a u term. We don't have that, okay. What have we lost? Well, if you looked at it as a wave system, so forget convection just for the minute, just look at the inertialess system, then there's only one set of waves. So you have these so-called magnetostrophic waves, which are interesting. They involve both the alpha in frequency, and the inertial frequency in a non-trivial manner here. And what you've lost are inertial waves. So computationally, it's quite good to get rid of inertial waves because they're a fast wave that you don't have to follow around. You see, an alternative idea, which is complementary, would have been to keep the Prandtl number in, but to make it large. So we could have kept, you might keep 1 over Prandtl number times inertia in this equation and make Prandtl number large, but then you are chasing fast waves around. Okay. So mathematically, as I said, it's quite a nice system mathematically, because you can do this, of course, you can do this rigorously. You can split the velocity into a thermal velocity and a magnetic velocity. And then you can split the momentum equation into a thermal equation and a magnetic equation. Okay, so you might regard, so at the beginning, you would just have thermal velocity, and then you would induce a magnetic velocity. The split here is not quite as separate as it looks, in the sense that, remember that we do have the heat equation. The heat equation depends on U, and U depends on UM. Okay, so through the magnetic field, you get into U, which you then get into theta, which does come back into here. So they're not absolutely separate. You could make them separate, and I'll come to that in a minute. So this is how we're going to classify our nonlinear dynamos. So roughly speaking, there's two sorts of dynamos. So you kick off with a flow, a convective flow, before you put the field in, and then the field grows and saturates. And of course, it changes the flow, but it can change the flow either significantly or not significantly. Now, if it doesn't change of course, it's got to change the flow to saturate the dynamo. But in terms of the scale, for example, you might get dynamos for which it's quite hard to tell the difference between the flow in the dynamo state and the flow in the convective state. We call those weak field dynamos. Okay, and we call strong field dynamos ones UM is significant. Okay, so a weak field dynamo, we would say UM is small. Of course, it's significant in that the little bit of smallness has saturated the dynamo, but but mainly it's all thermal. Or UM might be significant. Okay. Now this is a slightly unfortunate, well, there's the scope for confusion here, because this is a weak field, what we're calling a weak field dynamo and a strong field dynamo. They're not necessarily the same as this weak and strong field branches that I talked about in that little sketch of Roberts. I'll say a little bit more about that. It shouldn't really lead to confusion. So I'm going to talk about weak field dynamos, strong field dynamos. So weak field dynamos are where the flow at the end looks pretty much like the flow at the beginning. And a strong field dynamo is where the flow at the end looks very different to the flow at the beginning. Okay.
Okay, David, just a quick question.
Yes, please.
So the UT and UM are not orthogonal. No? I mean, what is the physical interpretation of UT and UM? I mean, I can see computationally why you are separating them, but do they mean something in terms of physical interpretation?
Well, they mean, I think they mean something in the sense that at the beginning, all you have is UT. You just have U thermal. And so you're inducing a magnetic velocity principally through the Lorentz force.
I see. Okay.
And then you can regard because of this inertialess assumption, you can regard your full velocity properly.
Okay.
Of course, you wouldn't be able to do this if you had a u dot grad u term, but having thrown that term away, there is a strict linear decomposition. So you can kind of keep track of thermally driven and magnetically driven. You see, if I add these two equations together, I get my full equation.
Right.
So that's how we think of it. It's a useful split into, I mean, it's not a unique split, of course, but it's a useful split into thermal and magnetically driven, which you can add together to get your full velocity, but only because, if you had a u dot grad u, of course, that would be meaningless.
Yes. Okay, let's go on. Okay, thanks.
Now you could, when I talked about this, I said the split wasn't quite as separate as it might look. If you wanted, you could define another problem in which the split is absolutely distinct. You could constrain your temperature by this equation, okay, where I don't have a U here now, I have a U thermal. So this is like prescribing my forcing, okay? The forcing is always the convective forcing. And so there will be a big difference, because in the full problem, you can get large scale flows in your thermal velocity because the magnetic field might be on a large scale, it might, and then through the temperature equation, you'll get large scale thermal temperatures, and then you'll get large scale thermal velocities. If you artificially constrain your problem such that the buoyancy force is prescribed, okay, then it's a different problem. It's an artificial problem, but it's a useful one in some sense. And so how you should think of what I'm calling here a thermokinematic problem is, it's almost like a forcing, but it's a convective forcing, but the magnetic field has no effect on that forcing. So I'm forcing a small scale flow. The field grows and saturates, but it can't change the thermal flow. Okay. So it's an artificial problem, but it's a useful one to compare with, I believe. So that's what we call a thermokinematic problem. I'm not going to say too much about that, but I'll say something. Okay, so these are, let me move on to what the flows and everything look like. So this is just convection at the moment, no magnetic field. The top, you're looking down on the flows, and these and the others, of course, are a slice, a vertical slice. So the onset of convection, this R is, remember, is the scaled Rayleigh number. It's the Rayleigh number. It's the conventional Rayleigh number, if you like, divided by the Ekman number. So the actual Rayleigh number is 500 times 10 to the 4. So that's 5 million here, okay, or 10 million here. But of course, you need a large Rayleigh number even to kick off convection, because you've got a small Ekman number. That's why people use this number, because it's a more order 1 number. So close to onset, you get columns almost, and these small scale features. As you increase the Rayleigh number at a fixed Ekman number, then of course you get you're essentially relaxing the so increasing the Rayleigh number is essentially relaxing the rotational constraint. So these little blobs here are essentially the Ekman to the 1/3 blobs that we saw earlier. As you increase the Rayleigh number, you get bigger blobs, and then you get sheets. Okay, so this is what inertialess convection looks like. Okay, then we're going to put a magnetic field into these flows.
Excuse me, David, what is lambda?
Oh, sorry, yes, thanks, Frank. Lambda is the aspect ratio. So these are not, yeah. So actually this box is actually 5 by 5 by 1. And this box is actually 2 by 2 by 1. So So yes, thanks for pointing that out. So the scales are not quite as you see them. This, you know, this box is only half the size of this box, or 2/5 the size of this box. Yeah. So this is putting this is what we might call a weak field dynamo, okay, which is the middle one of those plots. Oh no, it's the right hand one of those plots that we've just seen, and it does, you know, this is almost what you would expect such a plot to look like. The velocity goes down as the field goes up. Okay, the one thing which we can't really do is, as I said, that's why I put that warning in earlier, is you shouldn't really compare this number in terms and this number as an energy. In fact, I had to multiply this energy by a big number to get on the plot, but that's all because this energy comparison doesn't really make sense in this inertialess system. Okay, but in terms of U coming down and B going up, that is a standard picture that you will often see in dynamos. Okay, doesn't show too much really. So this is why I'm calling this one a weak field dynamo. So this is the final, this is the kinematic. So these are not at the same time, so I'm not asking you to compare side by side. I'm just pointing this out as a kind of how they look in terms of their general feature at the moment. So this is a snapshot of the kinematic flow, and this is a snapshot of the dynamic flow. Okay, when the dynamo has saturated, and there's a slight change. There's a slight change in scale. Yes, I think you can probably agree that the scale on the right hand side is slightly larger, but the general morphology is unchanged. Let's look in what that means. So in terms of the energy spectrum for the magnetic field, the solid line is the kinematic flow, and it's peaked here. Okay, so that's, you know, representing that cell size that we saw in the right hand of those pictures earlier. When it saturates, there is a move. There is motion on a larger scale. That's undeniable. And so that's what we said. You know, you've moved to a slightly larger scale. Okay. This is probably more revealing of what's of this decomposition kind of thing that Mahendra was asking about. This is the full velocity in the dynamical regime, the full vertical velocity at a certain time. And it is the sum, so these are all on the same scale, of course, it's the sum of the thermal velocity and the magnetic velocity. So, and orange here is 0. So white is one end, black is the other, and orange is in the middle. So you can see all of these features in W in the thermal velocity. Okay, and the magnetic velocity, of course, which is responsible for saturating the dynamo, just comes in certain places. So that's what I mean by a weak field dynamo. This is nearly all thermal velocity. Okay. You might say that's cheating. You might say, well, what if you did that same trick with the vorticity? Is it still as blatant as a decomposition? The answer is no, actually. So this is, you can forget the bottom left one. That's the three things that are at the same time here are top left, top right, and bottom right. So this is the full vorticity, the full vertical vorticity. This is the thermal vorticity, and this is the magnetic vorticity. So this is interesting, actually, because it shows that the magnetic vorticity, which is responsible for saturating this dynamo, essentially is all in the sharp scale features. Okay, so the thermal vorticity is a smeared out version of the full vorticity. If you add these two together, you'll get the full vorticity. Okay, so the decomposition is actually more revealing in the vorticity, as you might expect. What if we took the dynamo from the left-hand plot of those convection plots? So this one is more rotationally constrained, right? It's at the same Ekman number and a smaller Rayleigh number. So it's much more rotationally constrained. So even without doing anything except just plotting U squared, you can see that something different, manifestly different, is happening, right? This is the flow in the kinematic regime. The field grows, and interestingly, the flow goes up, and its temporal variation is much different as well. Okay, so what's going on here? So this is the kinematic flow that we've seen earlier, these little cells, and this is the dynamic velocity, the vertical velocity. Okay, not obviously not at the same time, these are just snapshots, but you can see a much larger scale has evolved in this right-hand one, and in this plot you can really see it. Okay, so this, I think, is quite a revealing picture for lots of reasons. So the solid line is the kinematic flow. You can see there's a very sharp peak at about 20, and that sharp peak is just these little guys. Okay, and when the dynamo saturates, whereas in the weak field regime there was a slight movement, there was a slight increase in large scale velocity. Here there is a huge increase in large scale velocity, right? It's gone up something like 4 orders of magnitude. So there's a movement to a much larger scale flow. There is also, and this is interesting, we'll come back to this, there is also an increase in the small scales. Okay, this is not the end of the computation, in case you're worried, in case you're thinking that's the small, we go up to about 500, and so this it's just, I'm just plotting to 100, but there is a interesting shift to larger scales and smaller scales. Okay, there's a real flattening at the end of the spectrum, and that's going to be important when if we think about Taylor's constraint, right? Because Taylor's constraint essentially wants to get rid of the viscous terms, Taylor solutions, and you can see that that might not be so good because we're shifting a lot of energy to small scales. I'll come back to that. So going back to our decomposition.
Excuse me, David, can I ask a question?
Please, Frank.
Here you have R, which is equal to 500, and on the next slide, 10 power 4. So how can you compare those cases?
Oh, well, depends what you mean. How can I compare? I'm comparing how they. So when yes, okay. So the first ones here were R equals 10 to the power 4. Yes, these ones. So these 10. Okay. So this is what I would call. So here the rotational constraint is not that strong. It's the same Ekman number, but a bigger Rayleigh number. So the rotational constraint is not as strong, and I'm showing this as an example of what I would call a weak field dynamo. So I'm showing it as an example where when the dynamo, the field grows and saturates, the morphology of the saturated state is not very different to the flow in the convective state. So I'm showing it as an example of what I would call a weak field dynamo. And I'm contrasting that with a flow, a dynamo at a lower Rayleigh number, as you say, so a more rotationally constrained dynamo, to show how the dynamo can be very different, how it can be what I would call a dynamic dynamo. So I'm essentially comparing. I'm putting forward these two types as two different types of dynamo.
Okay, I understand, but on the next slide.
Oh, have I even shown you the next slide?
Yeah, you showed this one.
Oh, I'm sorry. I'm sorry, Frank. Yeah, okay. That is a typo, isn't it? Yeah. Sorry, that was the quick answer. Sorry. Yes. That's a typo. Yes, thank you for pointing that out. No one else has. This is the one with R equals 10 to the 4, yeah? Yeah.
Okay.
And this should have said R equals 500.
Okay, I understand.
Thank you, Frank. You're more awake than I am. Thanks. Yeah, sorry, there was a quick answer. It's my fault. Yes, this is the R equals 500 one. I must change that. Yeah. Okay, so this is the decomposition. And this is the decomposition, the full velocity, the thermal velocity, and the magnetic velocity. And you can see that it's a bit of both, right? This is the full velocity, and you can see features in thermal and magnetic, which leads to the full velocity. Okay. Here's an example of what we would call a super strong field dynamo. So this is at a smaller Ekman number again. So this is yet more rotationally constrained. And now you can see that the full velocity is almost all magnetic. So this is an interesting sort of dynamo, right? Because the thermal velocity, of course, is crucial because the thermal velocity is driving the convection, okay? But it is both crucial and small, okay? In that the actual velocity is almost entirely magnetic, okay? The difference between the left and the right is the middle, but it's small, okay? All the strong features are in the magnetic velocity now, okay? I'll say more about that as well. Okay, just let me say this quickly, so I don't want to run out of time. But it relates to something that I said earlier. The actual field looks quite similar in these two cases for the weak and the strong. And so our conjecture is that our bifurcation is like this, whereas what we call strong field solutions are here, and what we call weak field solutions, that's why I said we have to be careful about branches, are up here, because we see a continuous transition between what we call weak field solutions and what we call strong field solutions. Okay, we don't get this branch. So it's interesting to compare with similar work that Emmanuel Dormy did, and he was essentially asking the same questions as we are, but Emmanuel took a slightly different perspective. He made his Prandtl number large, but kept it in. So he decreased the significance of his inertial terms through that, and he got that branch here, and indeed this as well. So we don't get that, so we assume that inertia is crucial for this branch that we would have had. Okay. Right. So now let me get on to what really matters. What people are bothered about is the balance of forces. We've already talked about Mach balance, Taylor states, and all this sort of stuff. Okay. So what one needs is when you do these dynamo calculations, you need to have a good way of comparing how big the forces are. Okay, and there is some discussion about how you should do this. Our take is that, okay, it's incompressible, it's Boussinesque. So pressure is, as you all know, pressure is a funny beast in Boussinesque or incompressible fluid dynamics. I mean, it's crucial, but it's crucial to make sure the flow is incompressible. And that there's actually no loss in curling the momentum equation and treating it, looking at the vorticity equation. Okay, there's no loss in incompressible fluid dynamics. There's no loss of information in using the vorticity equation. In some sense, that's nicer. It saves you having to bother with the pressure, because the pressure, you think, oh, the pressure, maybe it's big, but on the other hand, it's big because it's keeping something incompressible. So the vorticity equation is the sensible equation to look at mathematically. However, numerically, it's a pain because as we've seen, we've got these small scale fields, and you have to take the curl of the Lorentz force, And so you have to take the curl of J cross B, and you've already used all your resolution to get J. And if you curl again, you're in trouble, okay? Because the curl operator spectrally, for example, involves multiplication by a very high wave number. And so that's not a very numerically accurate thing to do. That's what we tried doing, first of all, and realized that that wasn't so sensible. So this is what we do. We perform something which is sort of equivalent, but certainly less common. So we project the equations onto their solenoidal components, which is something that those of you that solve equation, spectrally have probably used this. So if you just solve, suppose you're doing incompressible fluid dynamics, you might well use a projection operator. You advance U, and then you use a projection operator to just project the solenoidal component. You don't actually bother with the pressure, okay? And that's what we do. And why that's better is that the projection operator is much nicer, a much nicer computational operator than the curl operator. Okay, it doesn't introduce terms proportional to the wave number. Okay, at high wave number. And so this is what we do. We project the two equations. There's no projection operator here because it's already projected. UT is already solenoidal. But the buoyancy term and the Coriolis term and the Lorentz force are not solenoidal. And so all the non-solenoidal bits are going towards the grad P. We're not so fussed about those. We want the solenoidal bits. And so we project them out. And so it's a nice computational way of doing it. The only drawback is that it's not so intuitive. It's not what we're used to. And also, if you project, let's say, a vertical force, such as buoyancy, it will have the projection of the buoyancy will have a horizontal component. Okay, so it's not so, it's not so intuitive, but it is computationally nice. And so what we're going to look at is how big these terms are. This is really what everyone's interested in. How big are these terms? Can we get a balance, for example, between, if it were Taylor, we would throw away these viscous terms. Can you balance this and this and this and this? Okay, so this is the most important slide in this seminar, I think. There's a lot of results gone into what you might kind of bar charts. Okay, so I'm going to explain all of this, I hope, carefully. So what am I doing here? I'm looking at these two equations. Remember, this is our thermal equation. This is our magnetic velocity equation. Okay, we project them out. So there's 3 terms in each equation, but the vertical and the horizontal are worth looking at differently. So there's 12 terms to look at. And at the moment in this bar chart, I'm just looking at the size of them. I know you might argue, and that would be true, you might argue, oh, well, they're vectors, you better be careful about looking at their size. That we'll come to that. So at the moment, I'm just taking the size of all of, the size of all of these terms. So the red equation, how should I, the red equation is the thermal equation. The blue equation is the magnetic equation. The left-hand plots are vertical components. The right-hand plots are horizontal components. So let's look at the red first of all. So the red equation is the thermal equation. It has 3 bits: Coriolis, buoyancy, this Archimedean, and viscosity. For weak, strong, and super strong dynamos. And there is something very striking here that you can see, which is that as we get from strong to super strong, the viscous term gets really small. Yeah? So that's nice. So what does that say? It says that in this equation, in the super strong dynamo, this term doesn't matter. So you think, oh, okay, that's half a Taylor at least, right? We're balancing buoyancy and Coriolis. We're balancing them pretty well. Look at this. This is, you know, remember these, well, they have to add vectorially, but essentially these two are just offsetting each other. However, if we were going to get a full Taylor solution, this column would have to vanish. This is the magnetic viscous term. Well, this column and this column, right? That's this term. That's the E del squared U magnetic. That would have to vanish. And you can see that even as we come down to super strong fields where you might hope that you're getting into Taylor land, that there is no there's no reduction, no sizable reduction in the viscous term in the magnetic equation. Okay, and that's the crucial thing out of this to take. So if we went to this is what I'm saying. If we do we have Mach balance? No, we don't. We don't have Mach balance because we have a significant viscous term in the magnetic equations. We're not getting rid of this. So a Taylor state in this diagram, a Taylor state would look like this. It would look like red, red, nothing, but it would look like blue, blue, nothing, and blue, blue, nothing here. Okay. As I said, these are, I appreciate running a bit late. I'll just finish this. What I said was these are vectors, of course. And so it's worth looking at the vector, at the actual components. And this is kind of revealing. So this is good. This is a weak field dynamo. And a weak field dynamo is here, where Coriolis, Archimedean, and viscous, they're all playing a role. And so this is Coriolis, this is Archimedean, and the viscous is the difference between them. Okay, so the viscous will smooth, is the difference between these two. Okay, and they're kind of comparable in size. However, if we go to the strong field and look at the thermal and the strong, so what am I doing here now? I'm looking at this column, where at least in magnitude, it looked like I've got a balance between Coriolis and buoyancy and nothing in the viscosity. Now, is that true in reality? Yes. This is the Coriolis and this is the buoyancy. And these are almost the same. The slight difference between them is the viscous term. So we're kind of, you know, ignoring viscosity in the thermal equation is good. It's moved to large scales, and you could ignore it with impunity. What about the magnetic equation? So this is the Coriolis. This is the projection of the Coriolis term in the magnetic equation. And this is the projection of the magnetic term. And you can see that the difference between them is the viscous term, and that's huge, right? This is smooth, and this is anything but smooth. Okay, so the magnetic viscous term really matters. Now you say, okay, that's a weak field equation. That's not what people are bothered about. People are bothered about the strong field equation. This is the equivalent for the strong field case. So the left-hand side is the Coriolis of the magnetic velocity, the projection, and this right-hand side is the projection of the magnetic term. And they differ. They are not offset. You can't, at least in the parameter regime where we are, you cannot offset Coriolis with Lorentz. That's what this is saying. Okay. The difference between Coriolis and Lorentz, which is the viscous term, is significant. So I'm saying that if it were Taylor, I would offset J cross B projected against EZ cross UM, which is the Coriolis. And I can't. That's not what happens. I can offset buoyancy and Coriolis really well in the thermal equation. They are almost balanced. But in the magnetic equation, at least where we are, we're getting a strong viscous term. they are strong field solutions. They're very different to, you know, they have a large scale velocity and everything. That's just a blow up, but they don't, you can't get rid of the viscous term. Let me just say one thing about the artificial problem that I introduced, the thermokinematic problem. How does that really change compared to the full problem? So this is the full problem where we had this balance. The main thing to notice is that you can't, so these are exact same parameter values for the full problem and the kinematic problem. You can see that the thermal velocity is way weaker. Why is that? So this is this does tell us something about how dynamos saturate. So in the full problem, you get a large scale field component which can drive a large scale velocity, and the temperature gets large scale, and so the thermal velocity gets large scale until you offset the rotational constraint in the thermal velocity, which is why you get this very good balance and quite high numbers here. 60. 60 doesn't matter, but it matters compared to 20 odd. In this problem, what am I doing? This is an artificial problem of some interest, though. We're just, the convection doesn't change, right? The convection is just forced at small scales. The dynamo, okay, then it generates a field, and the field generates a flow, okay, and the velocity is the sum of the two. But the convective, I can't generate large scale thermal flows. And so relaxing the rotational constraint is much harder. So I don't get nearly so pronounced thermal velocities. Now, another way of looking at that is through this problem. So this is also revealing, I think. You might say, how, if you looked at these, if you're relaxing the rotational constraint, are you improving the convection? And the answer is yes, notably, because there's a lot of plots on here. The main ones are, this is what convection looks like. Okay, I've called it thermokinematic, but this is hydrodynamic. This is the heat flux versus depth. So like the Nusselt number, if you like. The heat flux versus depth with no magnetic field. Now we put in the field, in the strong field case this is, we get a heat flux from the magnetic velocity. We get a slightly reduced heat flux from the thermal velocity, but the overall heat flux has gone up hugely. It's gone up by about factor 2. So what you've done is you've relaxed the constraint on the convection. The dynamo has relaxed the constraint on the convection and actually made it a much more convectively efficient state. So these are very interesting nonlinear solutions. The dynamo changes the convection. It helps the convection, which in itself helps the dynamo. So what we haven't found is Taylor states. So what have we found? So we found weak and strong field solutions. Now our strong field solutions, we wouldn't say they're Mach, because in the magnetic component, they have to have the viscous term. In the thermal component, they don't. So in this, which is not a very snappy algorithm, acronym, sorry, what we say is that they are viscous magnetic Mach. Okay, so if you wanted to study a system that was slightly reduced from the full system, you would throw away viscosity in the thermal equation, but keep it in the magnetic. Now you might say, well, you just haven't found one. What if you found one? Would it be stable? We would argue in our regime, no, because if you constructed yourself a Taylor state, which by construction has to be large scale, then in our regime, it would be unstable to a small scale perturbation in the field. Okay, that's what we're finding. And you'd get small scale Lorentz forces, small scale flows, smaller scale fields, and viscous terms will kick in. So even if we, by sneaky means, constructed ourselves a Taylor state, we are in a regime where the small scale magnetic field would destroy it. Okay, so there's no hope. There's no hope of getting a Taylor state in the regime we are at the moment. Okay, so how might we find a Taylor state? So we are not far enough down the branch, is our feeling. So we would have to. So we are in a strong field branch. That's true. So we're not connected to the kinematic regime, but on our small scales, we are still generating small scale fields. And you could see that going way back to that plot that I showed where the small scales were coming up. You see, if that had been a Taylor state, then you don't have small scales in a Taylor state. Everything is large scale. So you can't generate small scales. It must be stable to small scale disturbances. So you've got to push yourself way down the branch until the magnetic Reynolds number where you are is small enough that it doesn't produce small scale perturbations. Okay, so that's what we're actually doing now. We're kind of heading left, heading down the branch to see if we can find something for which this viscous magnetic turn doesn't matter. Thank you. I'm sorry I'm overrun. Thank you very much for listening.
So thanks, David, for a very nice talk. So we covered a lot of ground, I could see.